Hi there, welcome to another video podcast. I'm going to have a look at electrical circuits in this video podcast. I don't think we'll cover internal resistance or resistivity. What we're going to cover is just the basics of circuits. What do we mean by current, PD and EMF. We'll go relatively quickly through this material. It's really a summary. It wouldn't be that easy to follow if you didn't know anything about electrical circuits. Where the energy comes from in a circuit is the battery. If we just imagine that being wired in to a component like a bulb. There we go. This is the positive side of the battery, so we imagine current coming out of this side of the battery. It flows round the circuit, through the bulb and back into the battery. The battery isn't making electricity, it's just causing it to flow around the circuit. Now you may know that in fact it's not positive charge that flows in a circuit. There are electrons which move the opposite way around a circuit. For the most part it's best to forget that, and if you're ever asked for the direction of the current, it's always from positive to negative. It's the direction of movement of positive charge carriers. We measure current in amps, and it's simply a measure, current, of the rate at which charge flows around the circuit. So we've got charge measured in coulombs divided by time measured in seconds give us the current, measured in amps. Symbol for units are amps, capital C, coulombs, S for seconds. Often might see it written the other way round. Q equals I times T. The amount of charge flown is the current times the time. If you get exam questions on this, worth just remembering there are of course 60 seconds in a minute and 3,000 seconds in an hour. A more complicated question is, what do we mean by voltage? And in my mind, the way I always think about this is we imagine a little bulb, maybe from a car, a 12-volt bulb, and that's going to be wired in next to a much larger bulb, an old-fashioned filament light bulb that's rated at say 240 volts. Now, you should know that for a series circuit the current is the same all the way around the circuit. That's because we've only got one route. Whatever leaves here from the power supply must go through here, and it must go through here. If I turn this on and both bulbs were illuminated at the correct voltage, and we'll talk about what that means in a moment, this bulb would be much, much brighter, much more powerful than this bulb. So how can that be? How can it be that the same current, and we imagine a current of 1 amp flowing through here, 1 amp goes through here, 1 coulomb per second, and then it goes through here, 1 coulomb per second, but here it gives out a lot more energy than here? And the answer is, it's the voltage, which is a measure of the amount of energy carried by each unit of charge. It's really a good idea to remember 1 volt means 1 joule per coulomb. So our 1 coulomb goes through here, and in 1 second that 1 joule would give out, 1 coulomb would give out 12 joules of energy. Here it would give out 240 joules of energy, because the potential difference is more. So potential difference is a measure of how many joules per coulomb are transferred out of the circuit. So where does that energy come from? Well, if you're familiar with series circuits, you'll probably realise the voltage across this component plus the voltage across this component must be equal to the voltage across the supply. So in this case, this would have to be a 252 volt supply, and that's the EMF, the electromotive force of the supply. It means the supply is giving each coulomb of charge 250 joules. Our coulomb of charge comes around the circuit, gives out 12 joules here, and gives out 240 joules here, and returns with less energy to collect more energy and go around the circuit again. That leads us to a couple of simple equations. The energy transferred in a circuit is equal to the charge multiplied by the voltage. This is the number of joules per coulomb. This is the number of coulombs. So if you multiply them together, it gives you the amount of energy transferred. If we divide both sides by time, energy divided by time is power, and charge divided by time is current. So the power of an electrical component is equal to the current multiplied by the voltage. Have a quick look now at a parallel circuit, and have a think about how the rules for the parallel circuit are slightly different. Okay, let's imagine this is a 6-volt supply, and we'll keep it nice and simple. We imagine we've got a current of 2 amps flowing down here. This is clearly the EMF, it's the energy given to the electricity, and we're giving the electricity 6 joules to each coulomb. Electricity flows down here, and here something important happens. It splits. Some of the charge goes that way and some of the charge goes that way. We've got the simple rule that the charge in this branch plus the charge in that branch must be equal, the current in that branch plus the current in that branch must be equal to the current in that branch. What about the voltage though? If we put a voltmeter in the circuit, try to measure the voltage across there, what would it read? Well, if you know about circuits, you'd probably realise straight away that the voltage across here and here is 6 volts. But we can use what we already now know about the meaning of potential difference in EMF to explain that. Each coulomb of charge is given 6 joules of energy. It comes round the circuit, it goes through this bulb, and it's the charge that goes this way. That's the only component that it goes through. So this component must use all 6 joules that the coulomb carries. It then goes back to get more energy. Similarly, the coulomb of charge which goes through that bulb, it only goes through that bulb. So that must be where the coulomb of charge gives out its energy. If we compare that, we go back to the previous circuit. The reason why the potential difference was split in a series circuit is each coulomb is now going through more than one component and must divide up where its energy is given out. You also might be curious about what's different about the construction of these bulbs. The simple thing to say is that there is more resistance. The filament in this bulb has got a greater resistance. And put simply, this bulb is giving out 20 times more energy than that bulb. So if we imagine a little coiled wire, the filament in this bulb is 20 times longer than the filament in this bulb. Therefore, it's got 20 times as much resistance and gives out 20 times energy. I think that will do for a quick introduction to circuits. We'll cover resistance and internal resistance and resistivity in other videos. Thank you.